We have learnt several sorting algorithms. We have looked at brute force algorithms like selection sort and bubble sort. We have looked at merge sort and quick sort. We know that merge sort in the best case as well as worst case and average case, and quick sort in the case of average case can give us n log n performance. Let's look at an actual case study of a problem of sorting a very large data set and some interesting numbers that have come up in that. So in our work recently we encountered a sorting problem where there was a very large file. This file had this many bytes, right? 800,007,719. Right? So that's about 17.8 GB, counting 1000 as a kilobyte, right? So that's a very large file, and this file had this many lines: 101, 241, 556 lines. That's about 101 million lines. Each line on an average was a string of length of 176 characters. So more than 100 million very long strings. Each string on an average was 176 characters long. And for some reason, for our research work, we had to sort this file. We had to sort all these strings. So how do we do this? In terms of the hardware we have a machine with 16 GB RAM and a Xeon 4-core kind of processor. So pretty good quality machine, but it had only 16 GB RAM, which is less than the size of the data that we are trying to sort. So initially we thought we would have to write our own code, but then we looked at the implementation of sort that's available in Linux, right, in particular on Ubuntu that we were using. And it turned out that if we read the man page of that, it actually implements merge sort, right? So it's going to give us n log n. And from our initial lessons in algorithm analysis, you know that n log n may be feasible for such a large data set. That is the number of elements we are trying to sort, and if we have an n squared kind of a situation, clearly that's not going to finish in any reasonable amount of time. Before we actually tried to sort this using the sort command in this operating system, we wanted to estimate how long it might take, right? So how do we do that? So we took a smaller file, a file of about 23.8 megabytes, a small subset of that, right? It's much smaller than 17 GB, and it had about 130,000 strings, right? Much smaller than the 100 million. And we sorted this using the same sort command, and it finished in 2 seconds. It was extremely fast. Now, assuming that it was an n log n algorithm, we did some simple extrapolation, and we thought this should take about 40 minutes. And we ran the thing, and surprisingly, in fact, it took only 44 minutes. So actually, the machine could sort these 101 million strings in 44 minutes, which was quite reasonable because we had to do it just once. It's not something that we are going to do repeatedly during runtime. So the interesting thing here is, during the execution, the memory usage was always less than 4 GB. How did it sort a 17 GB file using only 4 GB of RAM? Right? So if you read the details of how merge sort is implemented on these platforms, it turns out that it uses a number of temporary files. It never actually loads the entire data set into memory, because if the entire set of strings were loaded into memory, it would have needed at least 17.8 GB of RAM. right, or virtual memory extension of that when it goes beyond 16 GB. But that never happened. It was able to sort the entire file, entire data set using less than 4 GB of RAM, because we kept monitoring it on the system monitor continuously, and that was because it was writing the sub-problems, the results of the sub-problems into temporary files. So in spite of all the disk input-output operations involved in writing and reading those temporary files, it was able to, it's remarkable that it was able to sort this entire thing in 44 minutes. Now we thought, what would happen if we sort an already sorted file? So we took the result of this, which was another 17.8 GB file, which was now already sorted in ascending order, alphabetical order, and we sorted it again, right? So sorting an already sorted file, and that finished in 25 minutes. So in 25 minutes it was able to tell us that the file was already sorted. Well, it didn't quite say that, it produced another result which was identical to the input. So 44 minutes to sort an unsorted file and 25 minutes to sort an already sorted file. It will be interesting for you to go and find out why it did not take 44 minutes again. How was it able to sort it in only 25 minutes? Because the file was already sorted. Think about this, read about this, and you will find interesting things about how some of these algorithms are actually implemented in practice.